Okay. All right. Hi, welcome friends. Welcome friends. This is the video series where myself and my friend Noah, we learn and write some Rust. So this video series is going to be aimed at Rust beginners. In particular, we'll get into the introductions in just a moment here, but Noah and I are both client-side developers. We work in programming languages like Swift on iOS and JavaScript on the web. And we're just going to be talking about what Rust is going to be useful for these types of developers and sort of our unique perspective on that, typically because Rust is actually not aimed at client developers, really. And we'll talk about actually how that's not true, and that's sort of a false thing to think. So anyway, my name's Eric, and I work for a company named Notarize. I've been working in the industry for about 6 years, and I got into Rust maybe a few years ago. I read the Rust book, and I didn't get a chance to really write any real-world programs with it, but I was definitely super fascinated with the programming language. And then, as we will talk about later in this video, I got very excited about it because I actually thought, found a use case where Rust really shined. And I decided that I wanted to spread that knowledge around. And joining me, of course, is my friend Noah. Feel free to introduce yourself.
Hey, I'm Noah. I'm a developer at a company called Klaviyo in Boston. Eric and I actually used to work together at Notarize and also a previous company. And and as Eric said, we're both client developers. Been working for quite a while now in all different areas, but most recently I've been kind of focused in the mobile space. But yeah, these days I'm also doing some back end as well. So, but yeah, I've been hearing a lot about Rust, and Eric talks about it a lot, and so I'm interested to learn more about what are some of the strengths and weaknesses of Rust, and just find out more, basically.
Yeah.
I'm definitely more of the beginner than Eric, but
yeah. So I think
hopefully that will change.
I think most of our our target audience would roughly be in the same experience level with you, which is like I've seen some things on the internet about it, heard some people talk about it, but basically haven't written any real code, right?
Yeah. Basically,
okay.
I've heard. Yeah, basically
Okay.
us talking is the main of most of it.
Fantastic. Yeah, and I mean, I'm definitely not a Rust expert by any means. I would consider myself more in the intermediate level, right? So I have a sense of how things work, and I can write some meaningful programs, but there's some sort of parts of the programming language that I haven't even used and have really no idea what I'm doing. But so as we will talk about in just a moment here, we do have a working program that we want to right. achieve, right? And so I guess we can sort of dive right into that, which is that,
Cool.
So at my company, we use a technology called GraphQL, and we're not going to talk too much about GraphQL, but if you're not familiar with it, you can Google it and find out very easily what it is. But more or less, it's a way to make requests for JSON data. And so why that's important is as a client-side developer, you sort of specify from your backend or your kind of equivalent of a REST API what you would like from the backend, and the backend satisfies that exactly. And there's a schema that you are allowed to ask from. And so actually, to be honest with you, we can actually pull up a quick example just for reference of GitHub/Darius Scary. And so here's an example of what a GraphQL request might look like, the body of such thing. And in this exact example, we're asking for a comment, which has an author, maybe has some content, the text content. The author has a name and, some kind of picture avatar URL, right? And so this is what the client would write. And as a client-side developer, if you're using a programming language like TypeScript or Swift, of course you have these static types, and it would be really useful to be able to get the type of a response. And it turns out that GraphQL has a schema, so all of these fields, have a type associated with them, but you don't want to type that thing out by hand. It's kind of annoying
Right.
to write
Yeah.
these types by hand. So it'd be really, really nice if you had a tool that could read these GraphQL schemas or GraphQL queries that you wrote, and then just automatically using schema information generate this code for you, right?
Yeah, and I can attest to that. At the company we used to work at, we did have to do this by hand at one point, and it is not fun. So these kind of tools are great for, being able to generate this code for you.
Right, right. And so, as a a hardworking engineer, I was like, okay, this is annoying. What can we do about this problem, right? And so I started thinking about, well, what about some kind of like little CLI tool that can like basically, traverse your code repository, find all these GraphQL files, and then, you hand it some schema JSON, and it just, does this automatically, right? And so this sounds very much like a compiler, right? This is like, it reads some files and then it produces some other files as strings in response, right? And so at the time we were using a tool, it's the Apollo tool,
Right.
and it works great. This is a tool that you can get. It's in NPM, and it'll exactly do what you want. This is a code. This is a command you would run, and you can get type schema, right? You can get these type definitions. The problem is, it was like, for us, it was particularly slow. I think we just have a very large repository with lots of these files, and it just took a very, very long time. So I decided, okay, well, maybe, this isn't such a hard problem. Maybe we can just like, get something that works a little bit faster, maybe something that is parallel, right? Because this is like embarrassingly parallel, right? Like you have this whole file directory structure, and, there's many files, and you can all compile them in parallel, right? So I said, oh, okay, what kind of programming languages are out there that I can use? I didn't really want to use Node because of that parallelism stuff. I didn't really want to use JavaScript. So I decided, oh, okay, what about this Rust thing, right? And so Rust is particularly well suited for this problem, not only because Rust is a very low-level programming language in the sense that like the kind of output that you produce is on the order of magnitude of a programming language like C or C++, right? But, for instance, I, as a client developer, a sort of high-level business developer my entire career, I've always been sort of scared of programming languages like C and C++, just because, I don't have any experience in all those, like, sort of a C or C++ programmer has all these rules in their head about, like, oh, if I allocate memory, I have to make sure I clean it up, and, you read all these like terrible things about security flaws and Heartbleed and all this stuff.
Buffer
overflows. It's like I don't even, to be honest, I don't even know what a buffer overflow is, right? So I'm scared of this stuff, right? So what can I do instead, right? And so that's why I settled on Rust. I was like, okay, well, this seems like a programming language that can offer me sort of the speed and the parallelism that I might be able to expect from a programming language like C or C++, but as we will discover, Rust has some unique features that sort of empower the developer, in particular developers like me, who are maybe not so savvy with low-level memory, right, to be effective and write useful code, right?
Right. Makes sense.
Okay. So this is sort of our end game in this series. Is I think Noah and I have sort of decided that we will work up to this. This is already a working program, and this is available and is useful and does its thing. But we're going to start very, very small, right? And sort of work our way as we learn Rust up to a program like this.
Yeah, and we'll link this out in this show notes too.
Of course. All right. Any other comments you think are important, Noah, before we sort of dive in here?
No, I mean, I would just echo the sentiment of that, we use this tool also for Swift and for Kotlin.
This Apollo tool, you mean?
Yeah. Sorry, not your tool. But that basically was a big factor for our build time. So this will be probably a great thing to have once it, is working for other targets as well, and beyond TypeScript. So right.
So one disadvantage of my tool, for instance, is it only targets TypeScript right now. So if we can, through this video series, get more comfortable with Rust, Noah can go off on his merry way and actually add another target programming language like Swift. Okay.
Totally. Cool. All right, let's get to it.
All right. So I figured that our audience, Noah and I discussed before we started this video that who would be wanting to look at Rust, and we figured it might be somebody who is looking at other programming languages like Go. So this is we're just going to go through this program. This is a Go program, line by line. It's only 50 lines, and just sort of explain what it does. And we'll just make sure we draw some analogies to the compiler that I was just talking about. And we'll see how this program actually has some bugs. And these are actually memory safety bugs. And so Go is actually a unique language in that it's definitely a programming language that sort of caters and is in service of concurrent code. It has a lot of concurrency primitives built in, and it definitely prides itself on sort of easy concurrency. But like a lot of other programming language, this is certainly not a problem exclusive to Go. You can still shoot yourself in the foot if you're not careful. And so this is a very, very simple program. And as we go through this program, hopefully for most people who have tried to write concurrent code in the past, it'll be pretty obvious what the problem is. And especially, a Go programmer would be like, oh my gosh, what are you doing? We kind of had to, manufacture this problem on purpose. And while the problem is definitely very obvious in a program that's only 50 lines long, as your programs grows in size and complexity, these kinds of memory safety issues can be very subtle. It may not be obvious as it is here that you actually have a problem. And I think one of the very strong things about a programming language like Rust is it enables a lot of local reasoning, right? Which is a thing that most programming languages try to do in various ways. They give you, scopes and functions where you can think about just the, internals of my own function. Rust does the same thing, even when you're talking about things like concurrency. And so while you may be only thinking about the part of the code that you're working on, you can still have a lot of guarantees given to you by the compiler about your local reasoning. You're like, I'm not worried about some other code somewhere else in my 500,000 line repository, like blowing my code up somehow. Okay, all right. So what this program does is so it reads some file names from the command line. So we're skipping the first one because that's the program name, and then it makes a sum, an accumulator, so it starts at 0. And for each one of these file names, it's going to go and read that file.
Do you mind if I ask a little bit actually here?
Sure.
I'm not as familiar with Go.
Yeah.
So accumulator there, is that like a Go, or what is that actually?
Yeah. So I think this is
that up there? Oh, okay. It's like a little struct.
It's
okay,
a struct,
cool.
right.
So you're just like initializing a struct, is that right?
Correct. And it's this is
okay.
potentially a little bit contrived, right? Because even as a programmer, you'd be like, oh, why wouldn't I just use like the number itself, right? Like, why do I need this struct around it, right?
Right.
And so the reason that we did this potentially will become more clear when we start writing the
As
Rust.
we move.
Because we essentially want to take this program and we just want to rewrite it in Rust and like almost line by line and see how Rust helps us, right? Okay,
Cool.
so it's got this little, like, as you said, it's got this little int64 that is our sum, right?
Nice.
We're just initializing it to 0. So this done thing is a very Go specific thing. This will not exist in the Rust program. But ultimately, it's a way for each one of these threads to communicate back to the main thread when they're all done so that we can print the sum at the end.
Is that what they call it? Is that what we were talking about, the channel?
Yeah, so this is a channel. It's basically a message bus between threads.
Oh, okay.
And so, again, like this particular thing won't exist in the Rust version, although we could use a channel. Rust also has channels, but they won't be required. This is pretty much the only way I could sort of hack together like a join. This is like waiting for all threads to be finished, if that makes sense.
I see.
Yeah.
I see.
Okay, and let's just take a look at the accumulate thing. So the important thing here is right away, if you've written some concurrent programs in the past, you're starting to get nervous because this accum we are essentially sharing that memory with all of these threads. So Go, you just prefix before a function call, and that automatically starts that function in a Go thread.
Okay.
So if you're nervous by this line right here, that's a good feeling to have. You're probably someone who has written a lot of concurrent code, and you're like, oh boy, we're already getting in trouble, right?
So if you have two different threads reading from that memory at the same time, and maybe we're writing, you could have some kind of races there, right?
Exactly.
Maybe? Is that what you're getting at? Okay.
Yes. And so data races are a particular kind of memory safety, and they're a memory safety that Rust actually has some built-in primitives into the compiler, right? And so let's just finish this program real quick because it's pretty straightforward, right? Okay, so you open the file, you check for some errors, you make sure you close the file when you're done, you read the file's contents, turn it into a string. This is like cutting off. There's a new line character in these files. You convert it to an integer. You check for some errors again. And so here actually is the sort of the guts of the program and where the problem exists. And so I have put in some sleeps here just to make sure that when we run this program, we will get the actual problem. Because as you know, data races may or may not happen at runtime, right? They can be very subtle in these ways. And so this is going to sleep for some random amount of milliseconds between 0 and 20. It's going to read the current value of the accumulator. It's going to sleep some other amount of time, and then it's going to overwrite that data with the number we read from the file and the old number, and then it's just going to report that it's done. Okay, gotcha. Does that make sense?
Yeah, it makes sense to me. I guess one question I was thinking of while you were talking was like, so you mentioned like for each file we're going to get a new thread. Do you know if like does that mean like that operates on each core of your CPU, or would that?
Right, and this is definitely a question for your particular programming language, right? So like, so these are actually called what's called Go routines. Now I'm definitely not a Go programmer, so take what I say with a grain of salt. This is, but basically these are like green threads, and I believe the Go runtime will do its best to allocate those on as many cores as you have available. And you're not responsible for that scheduling or anything like this. The Go runtime sort of handles it for you. So in this particular programming language, you're correct. But even if you had, I think this is a very interesting point. I'm glad that you brought this up, Noah, is even if you only had one core, or even if you had a runtime that only scheduled one Go routine at a time, the important part here is, this is where the race part comes in, is the Go runtime may or may not unschedule your thread at any time. We're sort of making that effect more obvious by putting these sleeps in here.
Right.
But it can schedule or unschedule you at any time. Even if you are quote-unquote single-threaded, you're still concurrent. And so that these accumulates might be scheduled or unscheduled at any time. And depending on when they are unscheduled and scheduled, you may run into some difficulties here, right?
Gotcha.
And so that's definitely,
I mean, not cool, but
yeah. And that's definitely the tricky part of this is this sort of, there's probably a name for this, but this sort of, I need to read the current state and then update that state. That needs to be atomic, right? And in our programming, in this program, it's not, right? And we have no help from the compiler to enforce that atomicity, right? Like that's just.
Whereas Rust might like tell you like, hey, you're doing something bad there.
Exactly. Okay, so let's actually just try to run this program. So here it is in my editor. This is exactly the same program. We looked at it in the browser because I don't have any syntax highlighting, but this is exactly the same program. The only thing I have done is I have removed that little Go thing. So this is now officially 100% single-threaded and not concurrent. So we'll just run that program. So if I
had actually one other question there.
Sure.
So with the channel, this is just for my knowledge, like the channel part, do you still need that with the when you're not doing the Go routine, or you just always need that channel?
So it's not required to do concurrency in Go. It's just that I think the channel is the sort of idiomatic and built-in way for threads to communicate in Go. That's just the
Okay,
way in
cool.
which they do it. So again, like we have this main thread, so to speak. We actually have 1 plus the number of file name threads, right, so to speak. And we don't want to print the sum until we know that all of the threads have read their files.
Gotcha.
Does that make
Okay.
sense?
Okay.
That's what this is
Gotcha.
about. This is an excellent
Okay.
question, though. Okay,
Cool.
so again, this is exactly the same program. The only thing I have done is I've removed the concurrency, right? And I have some files here, 1, 2, and 3, and they just have, an integer in each one. So the sum of this should be 6, right? That's the expected result. That's the correct result. And so if I run this program without any concurrency, we should get 6. And that's great.
Cool.
Like that, that works every time, and we're very happy with that. But if I add that concurrency back here, so now again we're running these threads at the same time, and I start running this program, we start getting weird results. And so this is exactly what you were talking about, which is that we have a data race, right? And so probably these numbers are due to when and how those threads basically got scheduled to do this line, and who won, so to speak. The person who won is probably last to write the accumulator, right? And so this is the point I'm trying to make here, and this is not particularly isolated to Go as a programming language. It's a problem in lots of programming languages that as soon as you make your program concurrent, you have all these new concerns to think about. It's a bit of a shame that just by wanting to add concurrency, I got all these new problems, and I had no help sort of upgrading my program from non-concurrent to concurrent, right?
And I think also you don't know there's a problem until you ran it, right?
Yeah. Or sometimes so the weird thing is, I bet I wouldn't even be surprised. If I comment these schedules, I wouldn't even be surprised if we get the right answer a lot of the time. Oh, so Go doesn't like when you have stuff that you're not using.
Wow.
Yeah.
Well, thank you.
What's the other one is complaining about? Math Rand. Okay. Okay. So you can see that actually this is a concurrent version of the program, and it's seems like it's working, right? So this is a bit tricky and can be super subtle in that we don't actually know if there's a problem. Sometimes it can look like it is correct to us, right?
Yeah. So if we were doing maybe more significant work, without this artificial sleep, maybe, I don't know, maybe they were bigger files or more computation
or lots more
maybe
threads, right? So my particular machine has 16 cores and is probably running these all at the same time, and it might be more tricky when you only have 2, right? Or maybe you have I don't know, whatever. So we know this program is buggy, but we can't actually observe that, right? We don't. And I think that a lot of programmers, especially programmers who've written a lot of concurrent code, would look at this and be like, "Oh my gosh, you're sharing a pointer between threads. You're in trouble, buddy. You're already in trouble." But again, the point is that this can be super subtle in a large code base, right? And it's maybe obvious here, but it isn't always obvious.
To be fair, there are probably ways to handle this in maybe an okay way.
Yeah.
But
and I think
it's a little bit more work, and still you're not getting that, you're not getting any kind of signals from the compiler about it.
Yeah, and ironically, this program to work correctly is, I think, using one of those mechanisms you're talking about is channels, right? So channels are automatically atomic, right? So when you write to a channel or read from a channel, you're sort of guaranteed that atomicity, right? So, for instance, we could change this program such that instead of sharing the accumulator, every thread just pushes back the number that it read, and then the main thread manages the sum, right? And so your exclusivity on that accumulator is a single thread is maintaining this sum, right? So there are certainly lots of ways to do this, and lots of programming languages have lots of solutions. This is just one thing. And I don't want to pick on Go too much. I chose Go simply because it might be a programming language that people are looking at where they think Rust might be a competitor. And I also think that the code is going to look very similar in Rust. Yeah. So you can almost compare line by line almost exactly what's going on here.
Cool.
ironically, some programming languages, and I think that we actually talked about this a little bit before the show. Some programming languages, they handle this by like specifically outlawing things, right? So a lot of functional programming languages, basically their claim is they sort of solve this problem by not allowing you to mutate. So it's actually like not possible to write lines like this, so that you can never ever have a problem with threads, right?
That was like the functional programming language.
Yes,
right?
yes. You can also there are other programming languages like Erlang and some of those actor programming languages. So they allow mutation, but they don't allow sharing. So it's actually
Gotcha.
you're allowed to write lines like this, but you're not allowed to write lines like that, so to speak. So anyway, there are lots of solutions out there, and we're going to look at Rust's solution, which is relatively novel, in particular because it happens at compile time, which is kind of new to the game, at least outside the research space, outside the programming research, right?
Sweet.
All right, so let's get rid of this program. We don't need this anymore. So what I'm going to do here is, so if you're new to Rust, you can look up for your particular operating system how to install it. But I recommend a program called Rustup. And you can probably get this through, Brew or your package manager or whatever you want. And so what this is this is not Rust itself. This is just a toolchain installer. So it will automatically install the version of Rust that you want, and you can automatically update as new versions of Rust come out. Rust actually moves particularly fast for a programming language. I think releases are at every 6 weeks. And releases are relatively small, but they do happen quite frequently. And so it's nice to have this sort of toolchain manager that will keep you up to date. It will also automatically update itself and all kinds of stuff. So I recommend you look up for your particular operating system how to get this tool.
We're running Linux here though, so you just kind of installed this package. Is that right?
Yeah, I got it through my package manager. So
cool.
But I there's probably a shell script you can run on rustup.com or whatever it is. We'll probably put links in the video description.
Yeah, we should do that.
Yeah, where to get this stuff from. So once you have Rust up, and you have told it, hey, please install a compiler toolchain for me, which I have already done. It'll give you at least 2 binaries. So there's the Rust C. Let's just see what I got here. So I'm using Rust version 140. This is, I believe, the most recent one as of the recording of this video. But this is the compiler itself, and generally you don't actually invoke it directly that often, although you can, of course. Most people, what they use is a tool called Cargo. So again, this will be automatically installed by Rustup. And this is the tool that sort of, it's like a mix between make and npm and tools like this. It does the compilation, the building, it manages your dependencies for you. It automatically pulls all the, and this is just built in. This is the canonical way in Rust to build and run Rust code.
Okay.
And the other thing it does is it has some other niceties in it there for you. So for instance, if you're upgrading from one version to a next, there's some other commands like fix that will automatically upgrade things that may have changed or whatever. It's got lots of stuff built in. You could read about it, but we'll just use a few parts of it during this video. Most importantly, we can make a new Rust repository using cargo init. So what do you want to call this, Noah? Do you have a good name for this?
I guess for the purpose of this, maybe just come up with introduction or something, or I don't know, compiler part 1 or something.
Okay. Compiler part 1. Okay, so what this does is it tells me it created a new binary application inside this directory. So if I go in here, and just to show you what's in here, it automatically puts in some Git stuff.
Nice.
It probably reads from my Git config, recognizes that I'm a Git user, automatically puts some stuff in here. And I think there's cat.
What did you say TOML file is?
Yes, I haven't gotten quite there. I was just about to get there.
Oh, sorry.
But this has
jumping ahead.
a little hello world program, and then there's this cargo TOML file. So this is your configuration file. So TOML is a thing kind of like JSON or whatever. And this is how you configure cargo. So whenever you run cargo commands within a repository that has a cargo toml, it'll read certain things about, obviously, what the name of the binary is, the version number, who the authors are. So we should definitely put your name in this, and I will do that in a second. So this is an addition of the Rust programming language. By default, if it's a new thing, you use 2018, which is the current version. And of course, there's a subsection for any dependencies you might have. And we will certainly have at least one dependency as we write this thing. I think we need one for getting random numbers. So
is this? Yeah. Is toml its own format though? It's like kind of like, it looks almost like an INI file, or
I'm not sure. I think there's some guy named Tom. I'm not sure.
Okay.
But it stands for like super simple markup language or something. I'm not sure.
Okay. Cool.
Yeah.
Cool.
Okay. So let's just do another cargo command here, which is cargo run. And so what this does is it runs any binaries that you might have installed in your cargo toml. So we only have one called cargo part 1, and you can see that that's what it built. And just to demonstrate, there's this directory called target debug. So this is a debug build. So it has like extra symbols in it and stuff, and isn't quite as efficient as you would want it to be if you were releasing this for production use. But you can see that it builds this binary, and 2.6 megs for a hello world program isn't exactly like super great. But also this is a debug build. So I'm kind of curious if we run it with the release, like how big does it become this way? LL target release compiler. Okay, so it's still 2.6 megs. So this is a quite large hello world program, but that's okay. We're not here to learn about that.
Does it embed the runtime inside?
Yeah, that's actually a very good question. So what kind of runtime does Rust have? So there. Maybe if you're like writing assembly, you don't have any runtime, but basically, I mean, runtime is one of those things that, like, I think if we asked 100 different developers what a runtime is, we'd get like 100 different answers. Yeah. It's definitely overloaded, right?
Yeah.
But
I guess I just meant, like, do I need a lot of dependency? Like, could I put this on another Linux box, and would it run? What do I need to get to run, sort of thing?
Excellent question. So Rust has a relatively small runtime that is built into the binary, but it depends on what kind of libraries you link against. So I have a little bit of experience with this because this compiler that we've been talking about this entire show, we have a Mac build, because we have a lot of developers on Mac, but we also have a Linux developer or a Linux build for, like running it in CI or on the production server or whatever we need.
Gotcha.
And so the answer is it depends on what you link to. And that's a configuration of when you build your, this is like very particular. Like I will say that cross compilation, building for multiple targets, is pretty good in Rust, but perhaps not as good as, like, for instance, like programming language like Go, which very much prides itself on like these sort of statically linked binaries that can sort of be run anywhere. So as you see, we can do cargo run, and we get like a little hello world program. Also notice that cargo was smart here and said, oh, you've already built this thing, you haven't changed any files, so like I'm not going to compile again.
Gotcha.
So cargo's really, really nice. It basically does what you want it to, especially for the simple case. Like you should just use it.
Cool.
It also has sort of built-in support for all of the tools that you might want to use on a larger project, like linters, formatters, all that kind of stuff that are nice to haves, quality of life, for engineers and developers. That stuff is all pretty much built in, and you can pretty like Google whatever you want, and you'll find exactly what you need about cargo.
Gotcha.
All right, so let's start writing a program here. All right, so we've come back here. This is compiler part 1, right? So let's look at here. So we got this main RS program. So I think what I'm gonna do is maybe just put the Go program like next to us. We can just have like both up at the same time, and then we'll know exactly what they look like.
Okay.
So let's go here. Where was that? That was par go.go. So we can almost like translate this line by line, right? So we have a main function, right? So we need to get some file names, right? So in Rust we have bindings or variables exactly the same way as most programming languages. So Go, they have like this, I don't know what this is called, walrus operator or whatever it is, but whatever that thing is. But we have lets in Rust. Okay, so how you read from the file. So I have a reference file here, so I don't have to like look this stuff up in Google. But so they've got inf args, and again, this has the exact same thing that Go has, which is that the first argument to your program is the program name. So we're just going to skip that. And already we're like using some features. So like, let's say,
could I ask a few questions while you're typing?
Of course, of course.
Yeah. So a couple things I'm noticing here is use the word let. Does that indicate like a constant or?
Yeah, great question. So Rust has a concept of mutability, and this will actually certainly come up more prevalently as we get further into this program, which is that each binding has a mutable or non-mutable flavor, right? So by just saying let and let alone, we are saying that file name, the data structure that it points to is immutable, right? We're not going to mutate it in any way. It's a read-only, right? It's a read-only binding. And so if we wanted to change this, we would say mut, right? And so now we can actually do this. And to be clear, there's kind of a difference in programming languages between the binding is immutable, meaning I cannot reassign it, and the data structure that the binding is associated with is readable or writable, right? So I'm just going to bring this up from JavaScript, right? This is a comment, right? So in JavaScript, const, means that the binding is immutable, right? So it's impossible, or it's like a error for me to do something like this, right? I just can't change the binding. The binding always points at 3, and that's pretty much it, right?
Okay.
But then if I did something like this,
you could change that.
That's totally legal, right?
Right.
And so this specifically means that the binding is immutable. It always points to this object, but the object itself might be changeable, right?
Gotcha.
In Rust, it's only the thing that you're pointing at. So you can actually do something like this. Like that is also legal. So the binding is not immutable. It's just the data structure. So I can't do something like this. Like I don't know what you would do, but like right, like that's not allowed, right? That kind of thing. I would have to, and the compiler will complain if I try to. I would have to write something like this, right? Okay.
You couldn't like reassign again either, right?
I can reassign as long as I like say let again.
Oh, really?
That's
cool.
This is legal.
Okay.
So again, like
nice.
There's a difference between binding and the data structure, I guess, is what I'm trying to get at. And let is only talking about data structures. It's only talking about actual memory under the sheets.
Cool.
Okay.
And the other thing I was going to say was one thing I didn't realize is semicolons are there.
Yes.
Seems like which is a minor thing, but like that's interesting. They decided to keep those.
Yes, there are semicolons in Rust. Look out.
Cool.
Okay. All right.
Go for it.
Already we have used some. Let's get rid of this ugly JavaScript. We don't need this anymore. But we have used some features of Rust that like lots of programming languages have, but we haven't explained it all. So this into iter, what this does is whatever args is, we don't have to delve into whatever data structure that is, but I can turn it into an iterator. And so by turning it into an iterator, I automatically get all of these methods that iterators have, like skip and filter and map, and iterators are very much like I think they're almost identical to what they are in C++, but work very differently. JavaScript has generators, which are pretty close actually to what iterators are. I don't know. Does Swift have iterators? I'm not sure.
Yeah.
It does?
Yeah.
Okay, cool.
Yeah.
So anyway, the nice thing is that the iterator has this common interface that all iterators you can like skip certain numbers of them. You can filter them. You can map them, right? Okay, so this is actually file names, right? Okay, and I'm going to do exactly what I did in the other programming language, the Go program, which is I'm going to make this accumulator. Oops, okay, and we have to declare this. So I'll say struct, accumulator, sum, and I will do the exact same thing that I did in the, like that. And I'm going to do this weird thing, which I will explain in just a moment here. Okay. All right. So let's make sure this program compiles before we go any further. Oops, not run T. Okay, great. So Rust is it compiled it safely, but it's complaining that these are some variable names that we didn't actually use. And it says, "Oh, if you want me to stop complaining, you can underscore things." But
interesting.
We will get there, so we won't change. We won't fix that.
Okay.
So I built this data type. So a struct in Rust is almost identical, if not identical, to how structs work in Swift, I believe, but it's pretty much similar to this as well. It's a collection of properties, right? It's a collection of data fields. In our case, we only have one, and it's just our sum, right?
Gotcha.
This little guy here is not required, but you can automatically derive some interfaces that thing might implement. And this is useful if we ever want to print it for debugging purposes. Without this, we can't actually print it. So nothing in Rust implements anything by default, essentially. The built-in types have lots of things. Like, for instance, I64 already has derived debug. I can print the sum, but I can't print the accumulator, if that makes sense.
When you say print, you just mean like there's a function called print, I guess, or?
Yes, yeah.
Okay.
So we'll use that right away because we will need it eventually. Print line.
Print line.
Yeah. What is this called? It's called the accumulator. This one, the sum of the files. Here we go. The sum of the files.
So you're putting a explanation point on your print line?
Yes.
Does that mean anything, or?
Yes, I will get there in a second. Okay. Accum.sum. Let's make sure this compiles and works. Okay. All right. So it's printing correctly. If you see an exclamation point in Rust, this is actually not a function call. This is actually a macro. And so why is it a macro? Well, for a number of reasons, but most importantly, I can print any number of things I want in this format string here. And so this actually has a variable number of arguments. So we need the compiler to sort of hop in here and deal with a variable number of arguments. Functions cannot do that in Rust. So that's why we have a macro. I think at compile time, I don't know the implementation of print line, but I think at compile time, roughly what it's doing is it's literally parsing this string, making sure that the number of like little placeholders you have is equal to the number of things that you did. Now, just to show you for demonstration purposes, I think it looks like that. Let me just make sure. Yes. So this kind of placeholder with the question mark, that's the debug version of the data structure. And so the debug of the data structure looks like that, which is what we'd expect, right? But if I delete this line, it's going to complain and say like, "Oh, you can't do that. Accumulator cannot be formatted using this." Does that make sense?
Great.
Yeah.
That's really cool to know.
Yeah, and we don't necessarily need this, but if something goes wrong with our program at any time and we want to, print out what accumulator looks like at that moment, we can do it.
Cool.
All right. So let's keep going here. All right, so we're almost going to translate this line for line. You can say for file name in file names. Okay. That looks pretty reasonable, right?
Yeah, looks great.
And then we'll write this function called accumulator. Accumulate, right?
Accumulate.
And we're going to pass accum, and we're going to pass the file name.
Okay. You put a little modifier there, huh?
Yeah. So let's get this function going, and then we'll start talking about what the hell's going on.
Cool.
Accumulator. Accumulate. Okay. And then this is accum. and mutt accumulator. Okay, and it also takes a file name. Whoops, file name, which is a stir. And for now, I don't think I'm going to return anything. We don't need to do anything. I'm just going to print ln just to make sure this is working. We'll just print the file name.
Okay.
All right, let's make sure that this compiles. It probably doesn't. Okay, it says expected a stir and I found a string. Okay, so that's very easy. I just need to pop in one of these guys. Okay. All right, so this is exactly what you were asking about, homie, is, we tried to use a cum in a mutable way, and it says, you didn't declare it as a mutable binding, right? And it's about the data structure itself, right? So we said that no one was ever going to write to accumulator, but then down here we said, accumulate can write to it. So Rust complained. All right, let's make sure that compiles. Okay. Oh, okay. All right. So we're back to working, right?
Cool. There's like a little warning, but it's just because you're not using.
Yeah, we are not using this variable yet.
Okay.
Okay. So let's take a moment here and talk a little bit about what's going on here. So we've asked Rust, hey, that iterator that you had earlier, I want to iterate over it, right? So Rust has a built-in syntax. As long as the right-hand side of your in is an iterator, it'll just automatically do the right thing for you. And so for each file name, we're going to call this thing. And so this and mutt business is very similar to this and up here. And so you can think of it like address of. It's exactly, that's why they chose this character, I think. It's exactly like it is in Go and C and C++, where you don't want to actually give the file name to the function. You just want to give that function a reference to it. In Rust, we call them references. They're basically like pointers, right? And the difference between this one and this one, I don't want to dive too deeply into in this video. I want to just keep it simple. But roughly speaking, for like just like a quick rule of thumb, you can think of it like, this reference is not allowed to write to the string, and this reference is allowed to write to the accumulator. That's basically it. And that's where this mutt comes from, because it's mutable versus immutable. These are officially called immutable reference, mutable reference.
Gotcha.
Okay. That seems pretty good. And we will see how actually mutable reference is, while that is the correct name, that's what it's called in all the Rust literature and, probably the specification and all that stuff. It's a little bit misleading because you can actually still write to data structures with an immutable reference. We will see how actually this is very important here. It actually means more like exclusive access and non-exclusive access. Right, and so for threading and multi-threaded concurrent programs, this is really important, right? Because ultimately, as we talked about back here, the problem with this program is this thread does not have exclusive access, right? There's this non-exclusive access to this accumulator data structure, and that's a problem, right? Okay, so let's see here. So this is working, right? And let's actually add some arguments here. So I'm going to copy all those par file name data. I'm just going to put that right here. And so again, let me just make sure that data star. All right, so I have all these nice data files. Okay, and then if I say cargo run and I say data star.part, we're printing all the file names, which is exactly what we want. 1, 3, and 2.
Cool.
Okay. Feeling good thus far?
Yeah, it's pretty straightforward. It looks very similar to the other program too. So
yeah,
that's cool.
All right. So we got to do all this like file IO stuff. Let's go ahead and do that. And we got to parse some integers. So again, I'm going to be referencing my working program so I can go pretty quick here. Okay,
That's one thing I didn't ask you about in the other program, but
yes.
I didn't want to get too much into Go, but
yeah.
I saw that defer there. Does that mean it closes the file like at the end of the function?
Yes.
Okay.
That's an excellent question because Rust has the same thing, but as I'll explain in just a moment, it's kind of built in.
Oh, okay, cool.
Let's get here. So let's get some content. Let mut contents equals string.
So I actually I think and maybe this is something we could link to at the end of the show. But when I'm working on like a new language, like sometimes I don't know, like, oh, what's FS or
right. Yes.
Does Go have like a online sort of documentation that you can look at, or even local documentation that you get with like Cargo?
Yes. So you said Go there, but I think you meant Rust, right?
Oh yeah, sorry. Yes, Rust.
Yeah, so Rust has a idiomatic built-in, I think it's part of the spec even. They're called like doc comments. So you can do regular comments with just one, 2 slashes, but 3 comments is a like, that's a doc comment. And so
okay.
all of the standard library and basically any code that you get online from the Rust repository, it's called crates.io. It all has these doc comments, and documentation is automatically generated from this. So here's actually an example, docs.rs. This is all of the documentation that is automatically generated from those doc comments. So this is a GraphQL parser library that we actually use in QLC. I was reading something about it, but you can see that, like, you can write in example code, all kinds of stuff.
Nice.
It tells you all the structs and the functions that are available to you. This is like all built in and idiomatic. You can also run a local version of docs.rs that I think that generates this exact same stuff, but it's like on your file system, HTML files. So even if you don't have internet access or whatever, you can automatically generate this. It's probably also important for people who don't want to host their crate online, right? Maybe you have like some proprietary crate, but you still want docs for you and your developers. I believe it's just like Cargo Docs. Oh, just doc. Yeah. Oh, okay. So actually, it just built all the documentation in here somewhere. For this. Yeah, documenting. So it says I documented it, but like there's no documentation, so I don't know what the HTML looks like. It's probably basically empty. But it certainly will do things like, oh, I know that you have a struct called accumulator, right? Because it knows things about the code, even though I haven't put any doc comments, right?
Gotcha.
All right. Okay. All right, so let me keep going here. We're moving along.
So you've got the file contents, or you're about to get it, I guess. Yeah. You got it.
Yeah.
And then you're doing unwrap.
Yes, we can talk about that in just a moment here. So I need to annotate this. I64. Oops, that's not 64. Equals contents dot trim dot parse dot unwrap. Okay, so this unwrap business is almost, actually, to be honest with you, it basically is identical to these little if statements, because all of these things can fail, as you know, like maybe the file doesn't exist or whatever, I don't know, or maybe we're unable to read into the buffer for whatever reason, or of course maybe the parse doesn't work. Maybe it's not actually maybe it's just like random characters. It's not a number.
Would you say it's like is it like an optional kind of?
It is very similar to an optional. It's very similar. Okay. The only difference, in fact, between an optional and so the data structure that this returns you is a result, and it's very similar to an optional in that optional is like you have the thing or you have nothing, right?
Yeah.
Result is more like you have the thing or you
have
an error. Yeah. And so it's like a optional with information about the failure case, right?
So if you let's say you gave it a file that didn't exist, would it what would it do?
So this right now, this evaluates to a result, and that in and of itself is inert. It's totally fine. It's just the error case of the result. By virtue of calling unwrap, we're saying, well, if it's the success case, unwrap that value and just give me the success value, right? But if it's not, I just want you to panic. Just stop. The program can't proceed. It's basically exactly the same as this.
Is that like is it throw an exception? Or
good question.
Or is it like Rust, a different thing in Rust?
Yeah, so Rust does not have exceptions at all. All the error handling is done through the error types. So
Okay.
if you didn't want the program to just crash,
Yeah.
you would accumulate this error up. You would actually have this function, for instance, potentially return a result itself. And then, at the
Okay.
high level, we would handle that just like you would with exceptions, so to speak. But in our simple program, we don't actually care. We're just going to crash right away. It does have panics. And panics sort of operate in the same way as exceptions, as in the execution just immediately stops. But there's no way to like handle them. You can't like handle a panic and then keep going. It's like, no, the program is terminating.
Cool.
And so I think you can, I'm not 100% on this. I think you can hook into panics so that you can like properly clean up things and make sure you have a chance to do so. But you can't stop them. They're like a train that's just going to keep going,
Gotcha.
Okay, so which is exactly what we did in the Go program. We can actually probably have an entire video on just error handling in Rust, but we're going to keep it simple, right? Okay, so we're doing good. We open this file. We get some string. We read the value into that string. Again, this makes a lot of sense. We just talked about this a moment ago, is that I have to give this function mutable permissions, right, to write into that string, right? That's why I passed it this way, in the same way that I passed it this way, right? And just for your reference, by the way, if I don't do that, like let's say I try to pass the wrong kind of reference, oops, that's
it doesn't like it.
Yeah, cargo run. This is actually though that's
that too. Another problem.
That's a yeah. FS. Okay, let's see if we. Yeah. Okay. Oh, okay. So we need to import some more stuff here. Hold on. We're almost there. I gotta find out which is it. It's std io preload. Okay. Okay, io prelude star. Oops, man. I'm just
that's a funky looking one.
Yeah. Okay. Oh, okay. It says, the types differ in mutability. I expected an and mut string, and you passed me just an and, right? And that's not quite right. So it's actually a type error, right?
So it seemed like if I were to make a comment here, I would say you have to be pretty explicit about like the way you pass things to.
Yes. Yes.
This is a method in this case, right?
Correct. The file data, the file type, right, has a method called read to string, and it only takes, I guess it takes two arguments. One is the file itself, right, sort of an implicit one, right, and then it takes a string you want to write into, and you have to be very explicit about the mutability, right?
Gotcha.
Okay, let's keep going here. So we're doing good. Let's actually try to print the number.
So one thing I noticed too is parse. Does parse return an integer or an I-64 rather?
Right. Excellent question. So why did I write this? You mean? Is that what you're asking?
Yeah.
Yeah.
Well, like it did do some type inference there, or did it like call the right parse?
Yes,
You're
right on the money, buddy. Is that so? Parse is the return type is dynamic, right? So like you can parse many things, right? Like, did you mean parse a number? Did you mean parse a string? Did you mean parse, I don't know, some person object? Did you mean whatever, right? And so Rust normally infers the types of variables. Like, for instance, it knows the type of file is file, right? Because that's the only thing it can be. But if I get rid of this, Rust freaks out and says, I don't know. Yeah, I don't know, because there's a million different things that can be parsed. And so Rust will choose the correct version of parse, as you said, to do the I-64 version. Does that make sense?
That's great.
Okay. As you sort of pointed out here, in Rust, type declarations, like annotating your variable names, is optional, except where it's not, and the compiler will complain.
Okay.
Okay.
I see.
So we have a number, and now we're gonna do this sleep stuff. Okay. Use std. I think it's time is what we need. Oh, okay, so here's also where we're going to start using some third-party libraries, which is good. And I think we need thread. Yes, use std thread. All right. And so what I'm going to do here in cargo is I'm going to say vcargo toml, and I'm just going to add one. I'm going to say rand equals 0.7.3, I think is the current version. Let's see what happens. Cargo build. You can see that all I did was add the dependency in the version that I wanted, and as soon as I tried to build again, Cargo said, oh, you have a new dependency. I'll like go fetch that for you, download it, and compile it for you.
That's cool.
No
okay.
rand in the, oh, it's RNG. I'm foolish. RNG. Okay, all right. That was all I had to do. We still have some warnings. We have some unused stuff, but it's all compiling.
Okay.
Okay. So let's do basically what we did here, which is let cur equals accum.sum, and then we'll say accum.sum equals cur plus num, right? And then we'll do that. That's that thread sleeping sleep time duration from millis, okay? And this is going to be that RNG business, RNG dot generate range from 0 to 20. Okay, and we'll do the same thing here. And I think we need an RNG, mut RNG equals rand thread RNG. Okay, we need a semicolon there. Okay, let's make sure we're still compiling. Okay, built. Okay, run. Where's my data stuff? Oh, okay. All right.
Look at that.
Oh, look at that. We already did it. We did it. Our program is working.
All right, let's go home.
Yeah. So we can get rid of this print statement. Okay, so at this point, I think we actually basically have the exact same program that we had over here, but non-concurrent, right? There's no concurrency here. We don't have any threads, none of that.
Right.
We just have a thing that accumulates all the values. All right. Any questions that you can think of?
Which one's faster? Just kidding. No, I'm joking. Don't answer that. Don't answer. No, I think I kind of, I mean, I know we like really rushed through the like getting the dependencies, but I think that's pretty cool that that's kind of like all built in.
Yeah.
And I was a little surprised you have to get like a random number generator.
Yeah,
there's like a lot of times
there's not one in the standard library for some reason. I don't know.
It's interesting.
Yeah.
And also, but thread. So STD though, that's like all in there, right? Like,
yeah.
You don't need.
Yes.
Okay.
So
cool.
Interestingly enough, I mean, I can just touch on this real quick, is that Rust is also aimed at a lot of environments and programming use cases that like you actually may not want the standard library for various reasons. So you can actually opt into like what they call no STD, which basically means I don't want the standard library at all. And that might be because the standard library might have parts of it that require like an operating system or whatever. Okay. And so like if you want to write an operating system
or something.
Yeah, if you want to write like an operating system or embedded system device stuff, right? Like you probably can't use a lot of this stuff. And it's like I'm pretty sure it's as easy as like to opt into that, you just like say like no STD, like something like this, and then suddenly I don't know exactly what it is, but
sure,
yeah. But either way, as soon as you add that, the Rust compiler will start complaining about all these imports, and it'll say, "Oh shit, you can't use any of that stuff."
Yeah, but overall, I'd say it's like pretty similar to the other program. It's not that much different. So that's kind of cool. It's, it's not like it doesn't feel like super foreign compared to,
One thing I did want to touch on real quick is this business of this guy.
Call.
You had brought this up. So, Go has this kind of cool feature where you can say defer and then like some code that you want to run. And I think again, I'm not a Go person, but I think what this does is it basically schedules this routine to be run at the end of the function, at the end of the scope.
Right.
And so it's really nice for things that you want to like make sure get cleaned up when you're done. And you can like, I think that a Go person would look at this and be like, oh, this is very nice because I can put this file close right next to the open, and I like know that it's gonna like, I don't have to put the D structure like way down here, right? It's all the code is, again, this local reasoning, right? Like all these programming languages are trying to put, give you local reasoning, right? Rust actually does almost exactly the same thing, except you just don't like write the line. So every data structure in Rust, every data type can implement what's called drop in the same way that they can implement parse, in the same way that they can implement debug using these traits. And again, I don't want to delve too deeply into what this means, but essentially by a data type implementing drop, it's when that particular thing reaches the end of a scope. So for instance, file here goes out of scope right here, like almost the last line of this, so to speak. It's going to run that drop routine for you.
Oh.
And so the drop implementation is going to be that, right? Does that make sense?
Oh, that's interesting. Yeah, it sounds similar to something we do that's done in Swift. It's called automatic reference counting.
Yeah.
I believe it does a similar thing.
Oh,
where
yeah.
It like inserts.
Oh, yeah.
That stuff.
Definitely,
so that's cool.
Definitely true. You are definitely right about that. There's a lot of similarities between. I think that Rust and Swift are actually very close in
cool.
like a lot of their goals and how they work. It's almost like I think I'm not 100%, but I think the original author of Rust, the Mozilla guy, like he now works for Apple and he works on Swift. Like
that's funny.
They both like they steal ideas from each other. They're very similar.
Sure.
Yep.
All right.
Okay.
All right. So
let's
I think
try
the
to
only
make
thing
this...
left is like, oh, go ahead. Go ahead.
I was gonna say let's make this multi-threaded, right?
Yeah. Cool.
So I think we already have basically all of the imports that we need. I'm just double checking right here. Oh, we're gonna need one more thing. I'm going to write this line, and we won't explain it at all, but we will in just a moment. Arc and mutex. And so if you just like look at these names, this stands for atomic reference count, and this stands for mutex. Like you're like if you have written any concurrent code in the past, you're already like, oh my gosh, these are the data types that we're going to use for atomicity, right?
Okay.
And we're not going to use them yet. We're just going to import them because we will be using them eventually. And we'll just like see how Rust actually will complain at us until we do use them. Right. That's really what we want to demonstrate.
That's great.
So the only thing I'm going to do is I'm going to add a few more things here. This is going to be very similar to this channel business and this for loop. This is just waiting until all the threads will be done. So let's put it here. We'll say handlers equals vec. So vec is like a array of dynamic size. And then we'll say handlers dot push handler, and we'll make sure to include let handler equals thread spawn. Okay, and we'll call that, and we won't do anything else. And do we need anything else for this? Oh, right, we need to do the for handler. In handlers, we will call handler.join unwrap. Okay. So I think that's all we need to do. Oh, we have to make this mutable.
Mute.
Yeah. Oh. You got it. Okay. So we have this program, right? And we tried to make it multi-threaded. And oh my gosh, what is all this?
Oh.
Woo. So, okay, so it's complaining about unused imports, whatever. But really, this is the most important one, and I think this one as well. So these green ones are just notes. These are not actual errors. They're like the compiler trying to give you hints about what might be going on here. So all this stuff is like you kind of have to be familiar with Rust a little bit to really know what's going on. But this is the kind of crux of the problem, right? It says, oh, I can't borrow accum.sum as immutable because it's also borrowed as mutable. So what it's really saying here is the thing that you are like passing into these threads, you are kind of claiming here that this accumulate will have exclusive access to it. You're saying that like, oh, no other threads, no other like execution context, nothing will not be able to read or to write to this. It's just me, just this single like instance of accumulate. And we have actually violated that because we passed. Yeah, we've kind of violated that by passing it. Oh, so by the way, this is a closure in Rust, right? So closures, you could have arguments, right? But in our case, we don't have any arguments. It's just a function we're going to run, right?
Okay.
And Rust says, "Oh shit, you can't do this." There's like a bunch of reasons you can't, and like I don't want to spend too much time on understanding these errors, but my point is that we just tried to make this program multi-threaded. That's all we really did was add thread spawn, right? And immediately the compiler started complaining, and it said, "You can't fucking do this." So, how can we fix this? Yeah.
The cool part is that we did the same thing in Go and it didn't say anything. Right?
Exactly.
So
we had no idea, right?
That's in some way a positive thing.
Yes.
But I could see if I saw that compiling, I would be kind of freaked out too, because like that's a lot of errors for it's like hard to read. But.
Oh yeah. And so I think that if you were to try to understand the trade-off here, like what is Rust offering us, right, in the positive, which is that it's giving us some memory safety, and the kind of memory safety it's giving us is a little bit novel, right? It's data race and concurrency guarantees, right? That's the positive, but the negative, the trade-off there, as you said, is I think that this is like kind of hard to learn. Right? There's certainly a learning curve with Rust. This is like if you don't understand mutable borrows, which we barely even touched on in this video, all this stuff, you're going to be like, whoa, oh my goodness, right? So what I'm going to do here is a little bit hand wavy. And we'll explain it, but we'll just do this here. So I'm going to, instead of creating this accumulator just like sort of naked here, I'm going to wrap it in some atomic wrappers, right? And these wrappers are going to enforce that exclusivity in such a way that the type checker, the compiler, will be like, oh, because they're in these nice safe wrappers, you're allowed to pass it this way. So we'll just do that real quick. So I'll say arc new, and then I'll say mutex new, and then create the exact same accumulator within those two things. I'm going to let cloned equals accum.clone. Okay, and then instead of just accum, I'm going to pass cloned. Okay. And that seems pretty good. And so then this yep.
Does that have to be mutable too?
So no, actually, and I'll explain why when we get there.
Cool.
Let accum equals accum dot lock dot unwrap. Okay, so I think that this is now all done. And then over here, we're no longer accepting an exclusive reference to an accumulator. What we're actually accepting is a arc of a mutex of an accumulator. Okay. And now we're starting to get to the important part, which is we need to unlock this stuff. So we say let mut accum equals accum dot lock dot unwrap. Okay, and this actually no longer needs to be mutable. Okay, so what's going on here? I think there's one more error we need to fix. Run. Let's see what the complaint is. Oh, it says may outlive. Okay. Oh, right. We can just do this. Right. All right. Very, very straightforward.
Wow.
Okay, so now we have this.
Very-
Now we have this we have this program, and it's going to give us the correct answer every time.
Great.
So let's try to explain this just on the surface level. I don't want to go too deeply into this because I think each one of these things can sort of be a topic on its own. But I just want to give a taste to people who are like sort of like, oh, where's this going? Like, why did you have to do all this stuff? Well, basically what we did was, first of all, we put the accumulator inside of a mutex. And so the mutex is going to enforce this exclusive access for us. So whenever we call lock, we know that like from this line down, we have exclusive access. And that's why we're allowed to actually do the write and the read like this in this way. That can fail, so that's why we're doing this unwrap business. But in general, that's all we're doing here, right?
When would is that like a deadlock or something? Like if a lock fails
I think what actually happens is if one of the threads that has if there's like a panic here, like I think what actually happens is this lock.
Oh, because it doesn't unlock then, and so
there's like an error where like, oh, this mutex has essentially become poisoned. And it's like, well, you don't know if what's inside the mutex is in like a valid state because it could have panicked at any point, right?
Gotcha.
So I think that's when it fails. There's probably other reasons it fails. I'm not sure, but in general, we don't expect it in our program.
Okay.
And so it enforces this exclusive access and says, oh, okay, now you're allowed to do this. And here's another example of that defer, by the way, right? We don't have to write anything like this.
Yes, it's inserting it.
Yeah,
when it goes out of scope.
The drop implementation of mutex is unlock, essentially, right? Does that make sense? So it automatically closes the file and locks our mutex back up, or unlocks our mutex.
I guess I'd have one other question is you're kind of shadowing the accum there. Is that like a common practice though with like a mutex, whatever it's called?
I don't know. I just did it so I don't have to change these lines of code.
Okay, that's cool. Totally,
but you're right. Like,
I just want to check.
Maybe this is a bad name now. Maybe this should be like mutex accum or something, right? And then, I don't know. Whatever. Yeah.
Okay. I just curious. I haven't dealt with like low level stuff like this, so it's cool.
And the only other thing that I'm doing here, which might be a little weird, is not only am I wrapping that accumulator in this like atomic safe like structure that can del out this accumulator exclusively, but I'm also wrapping it in the RC stands for reference counting. So this is this would be an example of runtime reference counting and garbage collection, and essentially this has to do with Rust's sense of ownership. And it turns out that multiple threads, multiple parts of the code running concurrently, which may or may not end at different times, right? Like threads can go as long or as short as they need to, are going to be owning this accumulator. I should say the mutex that is holding the accumulator. And each one of those threads needs to report when they're done. And then when they're all done, then it's like, oh, okay, we're safely able to drop this mutex accumulator. No one needs it anymore. So there is also, just for reference, there is a RC, which is just the reference counter. The A part is, it's a reference counter that you can use with threads as well. And just to demonstrate, I believe, I'm not sure where RC is. Let's look it up. Rust, RC. Oh, it's RC Rust. Okay, cool. Let's grab that guy. RC. And if I try to use that version, for instance, it's going to start complaining and say, oh, okay. Oh, well, that's actually literally a compiler error. Let's try. Okay, it says cannot be sent between threads. And so this is actually another example of those traits in action. The RC data structure does not implement the traits that tell Rust, it's safe to use across threads.
Okay.
So again, it's another example of Rust trying to help us, right?
Cool.
Okay. All right. I think that's it. I don't think there's really anything else to be done.
I mean, we've got the same program going, except it actually works with multi-threading. Yeah. And I mean, it definitely was some hand waving, like you said. Yeah. But I think that's probably we're going to talk about later on.
Yeah.
So.
Yeah. And by the way, this is a very, very simple version of what that's compiler that we wants to do, right? You know, I think we said this earlier in the show, was that like, you know, that's essentially what this compiler is going to be doing. It's going to be traversing some data, some file system. For each file, it's going to be, you know, reading the contents of that file, producing some strings of its own, and potentially sharing some data between these threads concurrently, right? And there's going to be threads involved. And this is part of the reason that I think I chose Rust for this project is, you know, I wanted help with this stuff, right? I was like, you know, I don't know if I'm smart enough. I need some help, right?
Totally.
Okay. Anything else you want to end with before we wrap up?
I think all I'd want to say is like, if people have questions, like, would they, you're on Twitter, right? Or are you on Twitter?
Not on Twitter. I don't believe in Twitter.
Are you on anything?
GitHub. Send me a pull request.
A pull request. Okay. But yeah, so you can reach Eric on GitHub, and I'm on Twitter, ndurrell.
Yeah. We'll host this on GitHub.
Although,
we'll host this on GitHub. All the code will be available, including the Go implementation for reference.
You can ask me questions, and I'll probably just ask Eric what the answer is. So, but cool. All right. Well, this was fun, and yeah. Well, maybe we'll see what we'll do next.
All right.
After this.
All right.
Cool.
Stay frosty.
All right. Talk to you later.
Bye.
All right.